Hello, everyone. Welcome to video 3.2. Today, we're going to be focusing on elasticity, which I've mentioned, but I'm going to more carefully define it and show you how to calculate it. And it's important, as the background shows you, for thinking about things like life-saving drugs. And you can see that if you raise the price all the way up from $13.50 to $7.50, how exactly can you get away with such a dramatic price increase? So, and the hint is the answer is because the demand for life-saving drugs is pretty insensitive to how much you have to pay for it. So elasticity is this epsilon term, and it just simply means, for economists, sensitivity. So a percent change in X leads to a percent change in Y. And it helps make comparisons simple because no units are required at all. It's just a percent change in X leaves a percent change in Y. And most of the times this is a percent change in price leads to a percent change in quantity demanded or quantity supplied. And without an elasticity measure, it'd be hard to compare price sensitivity across goods that have much different prices, like candy bars and cars. So a 10% increase in a $1 candy bar is going from $1 to $1.10, where a 10% increase in the price of an $80,000 car goes from $80,000 to $88,000. So it's quite different across different goods. And some examples, like I mentioned earlier, would be prices on quantity, income on quantity, other good prices on quantity. And I got these other two applications. So one is a road construction. If you build another lane of road, how that affects vehicle miles traveled. And then another one that I'm working on right now would be NBA minutes played on salary. So I've got some generic ways to interpret these things for you laid out here. A 1% change represented by this delta in price leads to a Y% change in quantity demanded. A 1% change in income leads to a Z% change in quantity demanded. A 1% change in the price of good A leads to a W% change in the quantity demanded of good B. So that's the cross price one. And then actual examples from economics literature, a 1% change in road construction leads to a 1% or 1% increase in road construction leads to a 1% increase in vehicle miles traveled. So if you build new roads, you won't reduce congestion at all because people just drive more. And that means that the demand for driving with respect to the amount of road is unit elastic, or it's an elasticity of 1. Or a different one in the literature that I'm working on now is a 1% increase in minutes per game played in the NBA leads to a 2.5% increase in salary in the NBA. And so that just says that salary is very sensitive to the minutes per game, or the amount that you're utilized. And so those are kind of like math or wordy definitions. I think it's really easy to grasp the idea of elasticities looking at graphs of demand curves. So this is a perfectly elastic demand curve right here. It's completely horizontal without changing at all. So you can kind of guess that a perfectly inelastic curve, or a curve where you're not very sensitive to the price, is completely vertical. And so the intuition of this is that the curve on the left, you're infinitely price sensitive, and the curve on the right, you're infinitely price insensitive. And so we'll see how that looks. So let's see, if you raise the price from $2.50 to $7.50 for this perfectly elastic curve, then the demand goes to 0, because you buy 0 at any price above $2.50. Any price below $2.50, you buy all of it. Whereas if you're infinitely price insensitive and the price goes from $2.50 to $7.50, there's the same quantity demanded for all prices. At $2.50, you demand the quantity Q, and at $7.50, you demand quantity Q that are exactly the same. But these are just special cases of other elasticities where this panel down here is, there's a highly elastic curve where it's pretty horizontal, whereas this curve is highly inelastic because it's pretty vertical. And so you can see why this is if you look at the same price change that we showed you earlier. So in this highly elastic curve here on the bottom left, if price is $2.50 and it raises to $7.50, there's a large change in the quantity demanded. It goes all the way from the right all the way to the left of the graph to near the price or y-axis. And it goes from Q1, which is pretty large, to Q2, which is pretty small for this price raise. Now, if you do the inelastic curve and you raise the price from 250 to 750, the quantity demanded only goes from Q1 to Q2, which is a pretty small reduction in the quantity demanded for the same increase in price. And so we would say that this reduction of QD by a small amount means that this is an inelastic curve. And so now formally define elasticity or demand elasticity, price elasticity, mathematically. So we just have the percent change in quantity demanded over the percent change in price. It's called the own price elasticity, denoted by this epsilon p. And so if epsilon p, if this number is -2, that would mean a 1% change or increase in price reduces quantity demanded by 2%, and that would mean that it's elastic because it's greater than 1. Now, if elasticity p is -0.5, a 1% increase in price reduces quantity demanded by 0.5%, then we would say that this good is elastic. And so we can calculate this with the percent change formulas. And I'm going to simplify those a little bit for you. So on a linear demand curve, we know that elasticity is not constant. Using algebra, and I have this derivation in the appendix, you can show that the elasticity of price is the partial derivative of quantity demanded with respect to price times what the actual price and quantity demanded is on that curve. And let's break that down a little bit more. This is just the derivative, and this is just where you are on the curve. And on a linear demand curve, this is going to matter a lot. And so on a linear demand curve, we know that this term, this dqd over dp, is constant. It's just this negative b term. And so here's an example for you. Let's say we have this linear demand curve where the quantity demanded equals 286 minus 20p. So for every increase in 1 of price, you demand 20 less units. Let's say that the equilibrium in this is price $3.30 and quantity is 220. Now I want to find the elasticity at this equilibrium point. So we're going to get our handy dandy elasticity formula here, which I already have described. We know that dqd over dp is -20 by the exponent rule of differentiation. So if I want to take the derivative of this function here, then all I need to do is take the derivative of 286 with respect to p plus the derivative of -20p to the first power with respect to p. And I can do this noticing that the derivative of a constant is 0. So the derivative with respect to p of 286 is 0. And so now this is what I have, and I can just eliminate that 0. And then I have dqd over dp of -20p to the first power, and I need the exponent rule of differentiation to do this. So what I do is I multiply the constant factor 20 times the exponent 1, which is still just -20. And that's this part. And then I subtract 1 from the exponent, and I get p to the 0, which is just 1. And I know that the elasticity of price is this -20, which is the dqd dp, times where we are on the curve. And I've told you that where we are on the curve is 3.3 and 220. And so you just need to plug these in for the appropriate points. So we have -20 times 330 over 220. And we can solve that out and get the elasticity of price is -0.3. And we can interpret this as a 1% increase in price leads to a 0.3% reduction in quantity demanded at the equilibrium point. And so I just want to point out that a linear demand or a constant slope means that there's a non-constant elasticity. And the reason for that is not because the slope is changing. Like we said, there's a linear demand or constant slope. What changes is this P over QD part of the elasticity formula. I'm going to visualize that for you now. Let's plug in some numbers here. Let's say A equals 10 and B equals 1. And that's this corresponding demand curve over here. Let's see, at point A, we can notice that P over QD is very large because QD is small. So the denominator in this fraction is very small, and that means this term is going to infinity. And so there's a high elasticity near the price axis because this is the same and this is getting large. Now point B, P over QD, this term is very small. And so that means, or QD is very large, and that means that P over QD is going towards 0, and that means that this makes us highly inelastic near the quantity axis. And you're like, where does it change over from being inelastic to elastic? And on a linear demand curve, you can actually prove that that's at the midpoint, which is where there's unitary elasticity, or a 1% change in price leads to a 1% change in quantity demanded. And there's a few other elasticities that you should know about. One of those is income inelasticity, which is how the demand for good changes with income. And since in elasticity, it's still in percent terms, and it's governed or defined by this formula here, where the only difference is instead of this being price, now this is income. And Y stands for income. So let's say we have this demand curve here, which is defined in terms of price, other good prices, and income. Well, the partial derivative with respect to income is just 2, because we treat P, all the other P's as a constant because we're doing a partial derivative, and those all drop out of the partial derivative, and we just have 2 left. And so at a point on a curve, we can calculate the income elasticity. And so we're calling this point on this curve, income is 12.5, quantity is 220. And so plugging these numbers into our formula up here, we have 2, which is this, times 12.5 goes here, 2 over 220 goes here. We get that the incoming elasticity is approximately 0.114. And so that just means that a 1% increase in income leads to a 0.114% increase in quantity demanded at this particular point, which means that income is inelastic at this point on this curve. And then one other one, which I'll have you do in your homework to prove to yourself, is cross-price elasticity. So the elasticity with respect to other goods instead of own goods is how a demand for a good changes with a different goods prices. And this has implications for whether or not a good is a substitute or a complement, or both. And so it's still in percent terms because it's an elasticity. And it's defined by this formula here, where PO is the price of the other good. And that's all I have for elasticity. But there will be plenty of examples for you to practice calculating elasticity in the homework. And so thank you. You will see me in the next class. See you.